Salam and welcome everyone. So today we're going to be working on the question on the screen that says calculate the energy of a photon and energy per mole of photons for radiation of wavelength 200 nanometers, 150 picometers and 1.00 centimeters. Now the first thing you have to do is for us to note that we're given a question where we're told to find the change in energy as well as the energy per mole, which is also an unknown. And we were told that this question is we're told that when we're supposed to look for these things, we're not given any other information except that we're given the wavelength for the photon. So we're given the wavelength here, and at least the first question we see it's 200 nanometers. Then we have the second question 150, and the third question 1.00. Basically, we're given the wavelength, but we're not given any other information. Now, some of you may be wondering, how do you solve a question like this? Before I go into detail, I want to quickly mention that this is a question from the Atkins Physical Chemistry 11th edition, and this is from chapter 7, which deals with quantum theory, basically quantum chemistry, quantum mechanics. So that is where we got this question from, and I'm going to be doing more questions like that on this channel, not just thermodynamics anymore, but also other questions that involves knowledge of quantum mechanics as well as topics in that involve quantum theory, like the chapter 7. Now, it's important for you to know that the formula for the change in energy or the energy of photon is the Planck's constant times frequency, where h, the Planck constant, is a constant of value 6.626 times 10 raised to the power of 23 joule seconds. And then the frequency, which we're also not given, is also necessary. Now, what we're given is the wavelength. Now, you're going to be wondering, how can we use the knowledge of what we're given to be able to solve what we're not given, right? We'll be able to do that by comparing the wavelength lambda with the frequency v. So, what you just remember is that from your knowledge of physics, as well as even some topics in general chemistry, the formula that relates wavelength and frequency is the speed of light, which is just basically c is equals to lambda, which is wavelength times frequency, where c is the speed of light, okay, or velocity of light, which is simply 2.998 times 10 raised to the power of 8 meter per second. So now we have that. So we can write c in this form. So we can write the frequency, right? We can rewrite the frequency in this form here to equal c divided by lambda, where c is the speed of light and lambda is the wavelength. So basically, we can rewrite the formula for energy of photon to equal h times c divided by lambda. So this is the formula we're going to be using to solve each one of these questions. So the first thing you have to note is that we've successfully done that, so we can just simply start our work. So the first one, I, which is 200 nanometers ultraviolet, we already know the energy of photon will just be the lambda, and we know the value for lambda, h, to be 6.62 times 10 to the power of negative 34. I don't know why I said times 10 to the power of 23 joule seconds. I apologize. Let me quickly correct this. Planck's constant is 6.62 times 10 to the power of negative 34. So that was a big mistake on my part. So that's why you always have to look at your work as frequently as possible. So let me rewrite it right here, just so everyone is on the same page. Planck's constant is 6.626 times 10 to the power of negative 34 joules second. And then, of course, speed of light is 2.9998 times 10 raised to the power of 8 meter per second. So, of course, this one, so it would be Planck's constant times speed of light divided by lambda. So we would have 6.626 times 10 raised to the power of negative 34 joules second, okay, times 2.998 times 10 raised to the power of 8 meter per second divided by lambda, which is just 200 nanometer, 200 times 10 to the power of negative 9 meters. So we cancel out the seconds, cancel out the seconds, cancel out the meters, cancel out the meters. So the change in energy or energy of photon ends up becoming 6.626 times 10 to the power of negative 34 joules times 2.998 times 10 to the power of 8 divided by 200 divided by 10 to the power of negative 9. So when we input all of this information in the calculator, we end up getting 9.9324 times 10 raised to the power of negative 19. Yeah, this is basically what you get. Times 10 raised to the power of negative 19 joules. So you're going to be wondering, okay, this looks good. But then let's not forget that we are chemists and we're supposed to put our work in the lowest number of significant figures. So hence, what you end up doing is that we're going to rewrite this in terms of three sig figs. So our actual final answer will be changing energy is equal to 9.93. So three significant figures times 10 to the power of negative 19 joules. And this is basically our answer in three significant figures. So this is it. Now, remember, the question did not just ask us to solve for the energy of photon, we're also asked to solve the energy per mole of photons. It's very important for you to be very particular about what I'm about to teach you now. And the second part of the question is for us to find the energy per mole of photons. Whenever you're dealing with a question that says you should find maybe something per mole, for example, if you're told to solve gram per mole, right, which is basically molar mass, or you're told to find um heat capacity, molar heat capacity, or molar volume, or something like that, you already know that is the unit of something, right, divided by mole. So you may end up having to divide one quantity divided by mole. But in this particular case, we were not given the number of moles for energy, so we cannot just divide something by that, right? But one thing we know for our fundamental knowledge of chemistry is that 1 mole of a substance, of an ion, of an element, of an atom, of a molecule, of any particle is always going to be 6.022 times 10 raised to the power of 23, which is called Avogadro's number. So this was done in Gen Chem and also in elementary part of chemistry. So Avogadro's number is always going to be divided by mole, or the unit for Avogadro is just um 1 over mole, or mole raised to the power of negative 1. So of course now you're going to be thinking, how do I go from energy to energy per mole? Well, to go from energy of photon to energy per mole of photon, what you end up having is a situation where you do the energy per mole, right, is going to equal energy of photon changing E times the Avogadro's number, which is just 6.022 times 10 to the power of 23 divided by mole. So this is the formula that you need to solve it. So it's very important that you don't take for granted your fundamental level knowledge of chemistry, because it becomes very important in questions that may look indirect but they are actually quite direct. So the energy per mole of photons becomes 9.934 9324 times 10 raised to the power of negative 19 joules times 6.022 times 10 raised to the power of 23 divided by mole. So the energy per mole is just going to be 9.9324 times 10 raised to the power of negative 19 times 6.022 times 10 raised to the power of 23. You end up getting 5.981291 times 10 raised to the power of 5 joule per mole. So that is basically the answer to this question. And of course, we're a chemist, so we got to put it in the proper number of sig figs. So energy per mole of photon is just going to simply be 5.98 times 10 raised to the power of 5 joule per mole. Right? This is basically the answer to this question. And again, I just want to quickly mention that even though I basically put this work 9.938 in 3 sig figs. Even though I wanted to solve for energy per mole, I instead of using 9.93, I decided to use the raw values, because you need as much of the raw values as possible if you're still calculating. Then at the end of your calculation, you now round up. If you know that even though you've gotten an answer and you've rounded up, if that answer you've gotten is still needed in a calculator, you're supposed to use the raw value. That is how you do science, so that you get as much of an accurate data as possible. So yeah, that's it. So that's the first one. Now we have the second one. So if we go back to the question, we have a second wavelength to solve for. We've successfully done the first wavelength. Now we're going to the second. We have the second one, 150 picometers X-ray. So next one is 150 picometer X-ray. So remember, what is the formula? The change in energy, or energy of photon, let's just say energy of photon, is basically H times C divided by lambda. So the first formula that we derived here, so we're going to be using this one, H times C divided by lambda, where H is 6.626 times 10 to the power of negative 34 joules seconds, and C is going to be 2.998 times 10 to the power of 8 meter per second. So 6.626 times 10 raised to the power of negative 34 joule seconds times 2.998 times 10 raised to the power of 8 meter per second divided by 150 times 10 raised to the power of negative 12 meters. So you cancel out the meters, cancel out the meters, cancel out the seconds, cancel out the seconds. So the energy of photon becomes 6.626 times 10 raised to the power of negative 34 times 2.998 times 10 raised to the power of 8 divided by 150 times 10 raised to the power of negative 12. And when you do all of those calculations, you end up with 1.32432 times 10 raised to the power of negative 15 joules. So this is basically the answer to this particular question. But then our work is still not done. We're going to put it in the proper number of sig figs, which is going to be in 3 sig figs. So the change in energy, or energy of photon, is just simply 1.32 times 10 raised to the power of negative 15 joules. So this is basically the energy of a photon. Now, remember, our question is two-part. We also have to solve for the energy per mole of photons. So that's going to be the E mole here. So the E mole, remember, is just simply the change in energy, or the energy per mole of photons, times the Avogadro's number, or the Avogadro's constant. So E mole is just simply 1.32432, because we're going to use the raw value, times 10 raised to the power of negative 15 joules times the Avogadro's number, 6.022 times 10 raised to the power of 23 divided by mole. Okay, of course, we calculate, insert the information in our calculator. We end up doing 1.32432 times 10 to the power of negative 15 times 6.22 times 10 to the power of 23. When we multiply it together, we end up with 7.9751 times 10 raised to the power of 8 joule per mole. Now again, we're chemists. We're going to put it in the proper number of significant figures. So energy per mole is simply going to be 7.98 times 10 raised to the power of 8 joule per mole. And this is basically the answer to this question, to the question of 150 picometer wavelength. Now we're still not done. We still have one more question. The question is 1.00 centimeter microwave. So the third one is to solve for the wavelength 1.00 centimeter microwave. So the wavelength of a microwave. So we know the drill. The energy of photon is simply Hc divided by lambda, where C is what, 2.998 times 10 raised to the power of 8 meter per second. And you notice that I still like to rewrite like information, even though I've talked about it already. I do that so that as many students as possible understand what I'm doing and they get the best value from this video. So this is the value for speed of light C, and the value for H Planck's constant. The more I write it and the more you write in your notes, the more you memorize this constants value, so you don't always have to rely on being given in a test or an exam, because there's some professors that actually don't want to be giving you that, so that your brain is as active as possible. So 6.626 times 10 to the power of negative 34 joule seconds, right? This is another one. So the energy of photon is just simply 6.626 times 10 raised to the power of negative 34 joule seconds times 2.998 times 10 raised to the power of 8 meter per second divided by lambda, which is just 1.00 times 10 raised to the power of negative 2 meters. So you cancel out the seconds, cancel out the meters. So energy of photon will be 6.626 times 10 raised to the power of negative 34 joules times 2.998 times 10 raised to the power of 8 divided by 1.00 times 10 raised to the power of negative 2. We end up getting 1.98648 times 10 raised to the power of negative 23 joules. So this is basically the answer. But then we're chemists and we have to put our work in the proper number of sig figs. We have 1.00 centimeter. So that's a three sig figs value. So that will be 1.99, okay, times 10 raised to the power of negative 23 joules. So this is basically the energy of photon. Now, I want to also remind you that it's a two-part question where we're also supposed to find the energy per mole of photons. So, the energy per mole of photons would just be E mole is equal to the energy of a photon times the Avogadro's number. So, E mole simply going to be 1.98648 times 10 raised to the power of negative 23 joules times 6.022 times 10 raised to the power of 23 per mole. The energy per mole of photon, when you multiply two of them together, you end up getting 11.96258 joule per mole. Now, this is definitely this is definitely the answer to this. But then again, we have to put our work in three sig figs. So we're just going to end up with the energy per mole of photon is going to equal 12.0 joule per mole. So that is basically the answer to this question. You'd see now that we have successfully answered the question of each one of the wavelengths, and that basically means we're through with solving this question. So if you have any questions about this or any form of suggestions or concerns regarding how to improve this channel, please put in the comment section. I'm definitely here to listen to you, and if you have topics in mind that you want me to work on, also put it in the comment section. If you're a student struggling in any of your STEM related courses, whether you're in middle school, high school, or college, I'm the tutor for you. I help students succeed in their STEM related courses via mentorship and tutoring, as well as assist them in all aspects of improving life in academia. So if you have any questions, please email me. And if you would like to book a tutoring or mentorship session with me, please email me at shahabitutoring@gmail.com. I wish you guys all the very best. Assalamu alaikum wa rahmatullahi wa barakatuh.